Well, it's a great pleasure for me to introduce Professor Richter from the University of Regensburg. We've known each other for more than 3 decades as friends and colleagues. For the last decade, we've been collaborating. I spend summers in Regensburg. Our department has multiple connections to the University of Regensburg. Our chair, Brian Somm, also has a colleague he's collaborated with there. And of course, Regensburg has produced a pope. So the previous pope was a professor there of theology. So it's a well-known place. Professor Richter is the current president of the German Physical Society. He's been dean of physics there, and he's had many positions I don't want to talk about. I might mention I have photographic proof on my T-shirt of his time in the band of gypsies. That's not on his CV, but I've known him long enough to know about this. And he had wilder hair back then. But anyways, you might wonder how I got the president of the German Physical Society on my T-shirt, but I won't talk about that. Professor Richter started his PhD in Freiburg working with John Briggs and Dieter Winken, some very important people in the atomic physics community. And after that, he had a Humboldt Fellow when he moved to the University of Paris in Orsay. He then moved on to Augsburg and then had a 5-year position at the Max Planck Institute for the Physics of Complex Systems in Dresden as a junior research group leader, and eventually found his way as a professor at the University of Regensburg. And the thing I really want to emphasize in this introduction is the breadth of his research. If you look at his publications, you'll see he started out in atomic physics. He quickly added condensed matter physics and mesoscopic physics. He was doing quantum chaos as well, but to his expertise. But if you look at his papers, you'll see papers on graphene, topological insulators, all kinds of many-body physics, molecular electronics, quantum gravity now recently. He's done a little bit of work, fidelity studies. There's this huge breadth to his research interests. And so, he's kind of a modern day, someone who really knows a broad spectrum of things. So anyways, it's a great pleasure for me to have Professor Richter here. And today he's going to talk to us about quantum chaos and many-body systems and possibly controlling it and things like that. So join me in welcoming Professor Richter.
Yeah, Steve, thanks a lot for the kind introduction and also the invitation, of course. I'll try now to share my screen. Let me see. Good. Yeah, thanks again. Yeah, for the invitation, of course, it's always nicer to also for the audience to be on site to give a talk in presence. But the distance Germany to US is far. And I think on the other hand, it's nice to have Zoom these days and thereby the possibility to give these remote talks. Also, please interrupt me if you have questions. I hope to see this somewhere, but just otherwise, just ask questions directly. Yes, Steve mentioned topics. Today I won't discuss condensed matter, but rather indeed topics related to quantum chaos, which we have done together and earlier, as Steve was mentioning, in different fields in physics. Today it's about many-body physics. And to start with, I think I just would like to first thank the people with whom I'm working. And now I have to see whether, yes, now it works. I can go on. Okay, so there are 3 PhD students, Lukas, Josef, and Matthias, who have been involved in the results I will show. There's Juan Diego Urbina. Maybe a few of you know him. He is a colleague also here in theoretical physics in Regensburg, and our chairman, Steve. So why talking about many-body physics. I mean, this has a long tradition, and foundations of statistical mechanics and many-body physics, I think, were laid together also together with quantum mechanics. That's now nearly, 100 years ago. And that these topics kind of witness a recent rebirth, I think, has to do in particular with experimental physics, with the fact that you can now kind of create, you can design, and you can control and monitor many-body quantum systems. I mean, also synthetic quantum systems, and thereby also the interactions, to have strongly interacting but controlled systems. And here what you see is just a few examples. On the left-hand side, I hope you see the mouse here. Now you see a sketch of an optical lattice and a bunch of cold atoms inside that. So these are laser-tuned optical lattices. We will get back to this during my talk. Then on the right-hand side, Rydberg atomic arrays got famous recently because this is yet another platform for quantum computing. And then there are other systems like trapped ions here on the lower left, here integrated on chip again. And while the examples I showed here are more from the quantum optics, atomic physics side, then there's of course condensed matter, superconducting transmon qubits that we see on the lower right. Now, I think this is the reason why also on the theoretical side, if we think about activities, there's indeed in kind of since 10 years an emergent field that you might call many-body quantum dynamics and many-body quantum chaos. And this is nice because it is at the interface and kind of gluing together many subfields in theoretical physics that are usually or traditionally kind of delineated. And through these common interests, we really talk now to colleagues from completely different disciplines. And this includes quantum information, statistical physics, atomic physics, indeed, condensed matter, but even cosmology. And the common theme is, in a sense, well, far from equilibrium quantum dynamics, and also then related to that quantum chaos. And again, this has to do also with experimental applications. And there are many different sub-disciplines already of this field. Just as kind of key or buzzwords, there's many-body localization, also many-body quantum scars, another phenomenon that tries to localize a quantum state in an otherwise nearly ergodic system. Though I don't want to talk about those two aspects, but rather the last part. This looks a bit more traditional, a kind of equilibration, entropy increase. But due to these new methods in experimental physics and also theoretical techniques, we better understand now or try to understand how indeed non or far from equilibrium quantum system, many-body system evolves towards maybe equilibrium. And this means entanglement, growth, scrambling, and all that. And well, this is a bit what that sets the stage just as an outlook for the talk. I will first look back a bit to many-body classical chaos and the era of time. We'll see in a second what I mean by that. From this, we come then to probing the stability and the stability against perturbations of many-body systems, both on the classical and quantum sides. And to do so, we use, in a sense, methods to rewind time. You know, that a system might move forward in time under a perturbation. And if we can rewind time, then we can see through the overlap how susceptible the system has been towards perturbations. And then there's the third part, and I have to see whether there's time left. That's about kind of taking chaos not as an enemy that creates instability, but make use of chaos and quantum chaos, namely trying to use instability more generally as a resource for control. But let's see how far we get. Let's start with with things that all of us know to get into that. Think of equilibration in classical physics. Here, this ice cube that is melting. We have, of course, thermalization, that is the evolution towards thermodynamic equilibrium. And as we know, of course, this is typically an irreversible process. The entropy is increasing, might get to a maximum. And this is kind of a directed process. And now, nearly 100 years ago, in 1927, Arthur Eddington called that, or that there is, with such a directed process of entropy increase, this somehow defines an error of time. However, going back in time further to the 19th century, this notion has caused a controversy. And this goes, just as a reminder, many of you know this, of course, has been a controversy between Boltzmann and Loschmidt. So Boltzmann, of course, putting forward his concept of entropy increase, didn't agree with Loschmidt. He took the more conservative point of view, arguing that on a microscopic scale, of course, the laws of physics are time reversal invariant. So there is no time direction. And that was his point. How should this create a kind of a directed development and error of time then on a different scale? And I just will give one example, kind of a Gedanken experiment by Loschmidt to also set a bit the stage for what we will talk about, which has to do with instability then. Now, Loschmidt at that time was suggesting the following, which is now called Loschmidt's paradox. Think of now just classical particles, a bunch of n particles here starting commonly at a source. They move in a box here in a container. And then Loschmidt suggests to have, say, n demons for the n particles, that are able to freeze them instantaneously and then determine positions and velocities of those particles. And then Loschmidt would argue, okay, if you now just precisely reverse the velocities, so this is the lower right panel here, you see the arrows have just been changed in the direction. Then he argues, okay, then after twice the time, you wait just once the same time again, then, well, surprise, surprise, the particles will come back to the initial point if they had precisely the inverted directions and the same momenta and no perturbation. So Loschmidt would argue, or argued, that the knowledge of the n-particle positions and velocities were sufficient to either recover the past or predict the future with any precision. Well, this is kind of was the way he wanted to contradict Boltzmann. But of course, these days we know why this Gedanken experiment is simply doesn't reflect reality. And this has to do with dynamical many-body, say, classical chaos at this stage. This simply prevents you from doing that. And the reason for that is that if you have n particles and maybe n particles interacting with each other, then the slightest external perturbation, so this could be just taking a photo of the particles, perturbs them, and thereby, creates a slight changes in the initial conditions, and hence the system will not reconvene in this point. And of course, this has to do with chaos and has been often called in a bit bold way, is related to what is called the classical butterfly effect. And just as a reminder for that, that's shown here. This goes back to Ed Lawrence, 1972, I think, where he argued that, say, a flap of a butterfly in Brazil, I think that was his picture or story, can this cause a tornado in Texas? So the idea that the slightest perturbation of a system in an unstable nonlinear system exponentially increases and creates a tornado. And this still is an interesting, just as a kind of slight side remark. You see here this article from Tim Palmer, Physics Today last May. This article is interesting to read because just on the classical side, there are deep questions whether, as it says here, given the Navier-Stokes equation, it seems, I just read this now, that you cannot make predictions beyond a fixed time horizon, no matter how small the initial uncertainty. This is even one step further. I will discuss the butterfly effect more on the level that in a best way, in an unstable system, you have an exponential increase or change increase of deviations from the initial trajectory if you have a perturbation. Okay, so getting back to Loschmidt, this is simply one reason why his Gedanken experiment cannot simply be kind of realized. But then there's another aspect to that, more practical one, where you could say, well, Loschmidt, even if this works, how can you kind of rewind time? How can you invert the velocities of the particles at an instant to see an echo, so to say? And this brings me now already to quantum physics and to, on the other hand, to simpler systems and simpler dynamics. And we move further in time now and come to echoes and, I mean, to means to probe the stability of many body systems against perturbations. And this can be done through echoes. And as we later then see through another object that is called out-of-time order correlator, I will define this in way more detail later, or in short, OTOC or OTOC. But let's start with the echoes. And now we go back 70 years ago. Erwin Hahn realized the spin echo. Just again as a reminder, maybe and also for those who haven't seen this is just now from Wikipedia. So while it runs through, I just explain what you see here. So you have a system of spins that initially point right up. And in a magnetic field that's not shown here, that's also a vertical magnetic field. And the system starts with a pi-half pulse where the spins are kind of flipped. Then while they are kind of perpendicular to the magnetic field, and we just get back to that, here they start to rotate around the field, but the different spins having different environments have different velocities for the precession around the field. And now this pi pulse here reverts their direction such that they reconvene indeed at the same point, at the same time roughly. So what Hahn achieved here is indeed the first time reversal protocol. He just did what Loschmidt suggested, because the pi pulse changes the direction relative of the magnetic field to the spins, and thereby the direction of propagation in the quantum mechanical evolution. So formally, we have quantum mechanically, we have for a single spin, a spin Hamiltonian, and forward propagation by the operator e to the minus I h, the Hamiltonian of the spin, which is spin coupled to the magnetic field. And once the field flips, we get the minus sign turns into a sign. So he indeed rewinds time. And at the end, the echo measures the overlap and the size of the echo, whether during the course of the dynamics, there have been perturbations and all that. Now, this is, of course, famous and important also in applications in NMR, electron spin resonance, and so forth. However, what I would like to discuss a bit more now is that we have indeed here this rewinding of time, but this, maybe I should just get back to that second. Though we have many spins here, that is, say, in a material, many spins that are precessing, effectively, this is still an ensemble of single particle quantum systems. So they don't interact. And so the next stage would be now to ask, how can we generalize kind of aspects of this single particle spin echo to a many body system, possibly a many body spin system? And this is here just what I have here as a sketch. So think of a lattice, say a condensed matter system, a solid, where you have many spins that are coupled to each other. And now locally, you might kind of do a spin operation, or you measure the spin. This creates a kind of small perturbation. And then you can ask, is there something like a quantum butterfly effect? If we have a strongly interacting system that might be in a certain sense be chaotic, is there a concept like the classical butterfly effect of Lorentz that we saw 5 minutes ago? And the second question is, if so, how can we again use methods to rewind time to measure how susceptible the overall many-body system now is to perturbation? And now comes a bit of concepts. A theoretical concept, which is not so far away from this idea, is just the Heisenberg picture. And the Heisenberg operator picture tells us in this context, you would have an initial many-body spin state. And this is just this description of an operator W perturbing or acting on the system at time t. And you see, this looks like Hahn. You first have a forward propagation, then a small perturbation, and then backward propagation. And at the end, you take the overlap to see whether this is still small or big. And if W were 1, no perturbation, then you have just get a 1. And otherwise, you get a growth of the Heisenberg operator. Now, this has already kind of to do with observing instability. However, to make close connection between this classical butterfly effect and indeed a quantum butterfly effect, we have, for reasons that are a bit more difficult to explain at this stage, we have to consider a slightly more complicated object. And this brings us now to what is called out-of-time order correlator, OTOC. To this end, you see we have still here W of t appears here again in the upper branch. Think again of a state, but now we have two types of measurements. You would first have a first measurement with, say, time 0 with an operator V, later with W, and this gives you a new state, W of t V psi. And this you can compare now via an overlap with a state that you create if you just interchange V and W. So first you would have the W and then the V. And if you have now, if you take the overlap, that is the fidelity of these two states, then you get this object on the right side here. So initial state and either the overlap or you go back, forward and backward in time. That's the other way to interpret this object. At the end, it's a fidelity, it's a correlation function in time, but differently to usual correlation functions. Typically, we have two-point correlation functions, like in the Kubo formula and linear response, correlation between V at 0 and W at t. Here we go from 0 to t to 0 and t. So we go forward and backward in time. And that is why these types of correlation functions are called out-of-time order correlators. Okay, so far so good. This is the object we will consider in more detail because this helps us to quantify quantum mechanical instability. Now, sometimes people do not consider this correlator, but a related commutator, and that's shown here. So our correlator, again, sorry, is called F. This is this 4-point correlation function. F is here, and you see there, one can show there's a relation between the real part of F and an object that is now called C of t, which roughly includes commutators between V at 0 and W at t. And, well, they in a slightly, not precise way, we have kind of a square of these commutators. And this object turned out to be particularly important. This goes back to Larkin-Ovchinnikov, to condensed matter theory. That was theory of superconductivity in the late 60s, and was kind of reinvented or found again then by people from field theory, from cosmology, like Schenker Stanford. And it turns out that, and we will see in a second, that indeed this correlator of fidelity quantifies what one calls these days scrambling. That is, you initially you have, say, a many-body system here, spin system, you perturb it. This would be the first action of V at 0, but flips your spin, for instance. And then this perturbation will kind of spread out throughout the whole system through the huge high-dimensional Hilbert space of a many-body system. And as shown on the right-hand side, and this goes along with the spreading of quantum information that you put into the first measurement here, and also entanglement across the many-body system. And C of t allows to quantify this somehow. And this has, during the last 10 years, I mean, there has been a huge number of, it's a whole field considering this. So this paper by Schenker and Stanford, I think, has an order 1,000 citations now by now. And people talk about fast scramblers, many body systems that are particularly chaotic. And you see here the different fields. People look into black hole dynamics, or in condensed matter, their famous SYK model of strongly interacting Majorana particles, or more generally, and that is what I will focus on, chaotic many-body systems. Okay, so this looks like just a theoretical object, but has indeed also relevance now in quantum computing. And this is, you see this from this paper from 2021. It looks like a high energy physics paper with all the authors, but it is from quantum mechanics. You see it's Google research. You might see a few names from science. Kitaev is here. There's Igor Aliner, Hartmut Neven from Google. But I just would like to read here this highlighted sentence in the abstract. And they say, here, by measuring the time-dependent evolution and fluctuation of out-of-time order correlators, as I just described them, we experimentally investigate the dynamics of quantum scrambling on a 53-qubit quantum processor. So why that? Well, a quantum processor, this transmon, as I showed it at the beginning of my talk, this is a strongly, or should be a strongly entangled, strongly interacting many-body system. But at the same time, it might be unstable. And the OTOCs allow now to measure the instability. And this is an issue. So here, I just move away. Not sure whether you can. So here you see a paper from the Cologne group from theory. They challenge this a bit because they say this transmon platform might be challenged or might be unstable due to chaotic fluctuation. Sorry, was there a question?
No.
I heard some voice. Okay. I just go on, but please interrupt me otherwise. Anyhow, so you see, this has there is indeed these days it's important. It's not just a theoretical object that we consider here, but still, I mean, so far I just mentioned that this OCOT somehow measure chaos, and this I would like to explain in more detail now using a heuristic example, which is not strict, but better to understand. So we go back from many-body to a single particle, say in 3D, and into operators Q and P. So we first compute here or replace the quantum mechanical commutator between P and Q, between the operators, by the classical Poisson bracket times I h bar. So here you do a kind of a semi-classical replacement. Quantum physics is still involved. H bar is still Planck's constant is there. But now you can compute just by using the definition of a Poisson bracket here the relation between the initial momentum and the final Q. So, and it turns out to be dq final over dq initial. Dq final over dq initial. That's what comes out. And this means if you think of classical chaos now, so we went from quantum mechanics to classical physics, then this ratio just tells you if I change my initial condition slightly, how does my final Q changes? And in a chaotic system, this is exponentially sensitive. So this will exponentially increase with time. And the quantity that describes the growth is the classical Lyapunov exponent lambda. So here we see now, if we take the square, as I showed earlier, to get now to the out of time order commutator, we have to square this object, and we get a new object which has a quantum part through Planck's constant and the classical side. And this is now really interesting because we see here directly that on the one hand, you can, on the quantum mechanical side, compute this or measure this object. And this equation tells you that indeed, we expect an initial exponential growth of this quantum object that is governed by a classical quantity, the Lyapunov exponent. So we have a direct measure of, so OTOCs allow us to directly measure the chaoticity of a quantum system in the very sense. And it's important to say, often people talk about chaos in many-body physics, but one has to say what means chaos. And here it is well defined through classical chaos and the Lyapunov exponent. Now, so far so good, but there's one aspect now that's important. Here I explained this just for a simple single particle system. But now we have to go back to many-body. And for many-body system, it's not so easy to say what's the Lyapunov exponent. And you cannot simply do this heuristic derivation as I showed it here. And I won't show you the derivation later, but I would like in the following include a certain conceptual part of my talk. And this has to do now with semiclassical physics, to connect classical and quantum physics, but on now later on a many-body footing. So we go to Feynman. So we start with a Feynman path integral without discussing here the details. This is on the left-hand side, here we start with single particle. A single particle propagator in configuration space from initial to final points as a sum or an integral over all Feynman paths. And in the semiclassical limit, you can approximate this by now a sum, maybe a huge sum over classical objects, classical paths. However, they are weighted, you have a classical amplitude with phases. And the phases is given by the ratio between the classical action along a path, that is PdQ, and Planck's constant. And in the simplest case, if you have just three dynamics, then PdQ is just, this ratio is just the length of the classical orbit or trajectory divided by the de Broglie wavelength. That enters through the de Broglie relation, comes into play through the momentum here. So we see here that the ratio between the classical action and h bar is geometrically here something like the ratio between the path length or the system size and the de Broglie wavelength, the quantum mechanical wavelength. And in the semiclassical limit, the wavelength is short and the ratio is big. And in this limit, we see now that using this approximation means we use only classical paths. However, we have interference through this exponent here. And that's important. This creates wave interference and allows to describe quantum mechanical effects. Now, to explain how such a sum works, let's go back to the simplest case. So we have a single particle in configuration space and just two paths, namely just the textbook version of the double slit experiment. We have two paths in our final sum. They interfere and give the interference pattern. That's boring and good and well known. However, one might change the system slightly, and then it gets way more complicated. I would like to show how to get from two-path interference, as shown here, to multi-path interference. And this you get by just closing the system here. That means here, these paths that are just back reflected, usually, they are captured. They might here scatter around and finally, however, leave the system and also will change the interference pattern. So the question would be, or maybe you might think of now, what do you expect here? How will the screen, the interference pattern on the screen look like, given that you capture all these paths and you have indeed multi-path wave interference in the sense of Feynman? This is not such an easy question, but interesting that such a simple change in the textbook version creates this, this issue. There have been numerics and so on, experiments. What I just want to make it short. One can show that the answer depends on how the cavity looks like. If this would be, for instance, a rectangular cavity, then you have kind of bundles of orbits with correlated phases that move around and interfere. And then you still see something which looks like the two-slit interference experiment. However, if you have many chaotic paths or light rays that dephase show kind of self-dephasing because you have so many with different phases, then you get kind of such a Lorentzian curve. So this should just show, for a simple example, how to get from two to multipath wave interference. This you can, however, happens usually also in a system without changing here the system by closing the box. And this is the next transparency, which is a bit busy, but let me explain what I mean here. So there comes into play an important time scale, which is called Ehrenfest time, or these days scrambling time. So think again of a, say, wave packet now in a closed billiard with such a kind of a wall which is slightly bended. And now you can just compute numerically by solving the time-dependent Schrödinger equation how this wave packet will evolve if you launch it to the right. From here, this will be back reflected, and after a few bounces, you get a complicated interference pattern as seen here in the lower row. And now you can ask, how can I describe in a Feynman sense, say, propagation and interference from a point here, initial point, Qi, to a final point somewhere here. So we have to sum over all paths. And here comes time into play. At short time scales, at the beginning, there's just one path that will describe the whole quantum mechanical system. But after a few reflections, you need many, many paths to describe really interference. And there's now a time scale, the Ehrenfest time, as defined here below, that separates the wave packet evolution following classical dynamics, just given by one path, more or less, from timescales dominated by wave interference, where you need many, many paths. And this timescale you can compute or estimate. So think of a classical swarm of particles, of the size here in configuration space of lambda de Broglie. Then due to classical chaos, here's the Lyapunov exponent, after a timescale tau e, this will expand on the classical side up to a scale of the system size L. And then you can resolve this equation for tau e, and you see tau depends on 1 over the Lyapunov exponent, which is a classical quantity. Here classical chaos enters, times the log between L and lambda de Broglie. And that's what we had earlier. That is just this ratio between classical action and h bar. So here quantum mechanics enters. And if in the semi-classical limit, this gets smaller and smaller, and thereby the log bigger and bigger. So lambda gets smaller, or the log bigger, and thereby also this Ehrenfest time gets bigger and bigger. So this describes the crossover from single, say, kind of classical dynamics to many body, wave interference is described only by many paths. So to summarize this conceptual part here, what I described so far is, so I could just have this, I can draw here the horizontal axis. This describes me, this is just given by the ratio between this classical S, action S, and Planck's constant. So this goes from the quantum regime to more and more semi-classical or classical regimes. And the vertical axis is just my particle number. At the moment, we are just one particle in our billiard, as here. So if we go to larger and larger S over H bar, vice versa, h bar over s tends to 0, that's just a classical extreme limit. That's a limit where we have then nonlinear, possibly chaotic classical particle dynamics. On the left-hand side, we have wave functions and the Schrödinger equation. But in between, there's a semi-classical regime that I was discussing in terms of paths that is capable to describe wave interference for a single particle system. And this here, this orange part or red part, where I write single particle quantum chaos, this has been a field over decades during the last 50 years or so, where people have considered indeed the imprint of chaos in single particle wave dynamics. And our chairman has their foundational contributions to this field. However, here we would like to understand many body dynamics and many body chaos. So what happens if we increase the particle number? In principle, we could say, well, we'd go just here for fixed n to the right again. But it turns out that another limit is way more interesting, and this is what I show here. What we do here is to lift everything from the level of, say, first quantization and Schrödinger equation to second quantization. And then we would start, and I should mention also that 1 over the particle number is now our effective h bar, or n is 1 over h bar effective. So if we increase our particle numbers, we get more and more classical in a sense, and reach at the end a limit that is known as the thermodynamic limit, where indeed quantum fields given by field operators, the deep quantum regime of quantum field theory, merge into nonlinear wave equations. So from the perspective of second quantization, wave equations are considered as classical, and if they're nonlinear, they might be unstable, and this will be important. And again, in between, there's a semiclassical regime of path interference. But now it's not a path in configuration space, but in many-body Hilbert space. And interference is no longer just wave interference, but genuine quantum many-body interference. And that's what we are after in the following. So there are two notions of classicality, and we are interested now in the limit of large n, corresponding to another limit or aspect of semi-classical motion. This is sometimes difficult to understand at first glance. So let me give another example to make the correspondence more clear. Think of a triple slit. Then we have a triple path interference in single particle space and configuration space. The complement now to that, the analogon to that in a many-body system is what is shown here. And now I come back to my optical lattices. Think of atoms here and particles in there here at different sites of an optical lattice. This can be described in terms of Fock states with particle number, occupation numbers in the different sites. And think of a simple example, just 3 sites here. The initial many-body state is 130, as shown here. And then you have a quantum propagation from such a state to a final state 211, as an example. But there's not just one path. As we had here 3 paths for the single particle in configuration space to a new state here, we have now 3 complex, difficult, high-dimensional paths in this high-dimensional Fock space or Hilbert space, leading always to the same final configuration, but those 3 paths interfere. And each path is composed of single particle trajectories, so to say, if you wish. So this means we have more complicated, more abstract paths, and we should think of dynamics now in many-body Fock or Hilbert space. And this will, what we check now kind of as numerically for the model. So we have this is again the optical lattice. We take just 4 sites, and thereby we can now compute the quantum mechanical dynamics. And I have to show one example here of a Bose-Hubbard system. This is now if we have bosonic atoms that might interact if they are at the same site here, or they might hop That's the kinetic part, or there might be a chemical potential locally. These are parts that enter into the many-body Bose-Hubbard Hamiltonian. Many of you might have seen this in the bosonic or fermionic way. We have on-site interaction U and hopping J, and you can, however, by rescale the system, absorb this in a common parameter gamma. If gamma is of order 1, we have a strongly interacting, as we will see, chaotic many-body system. And the interactions enter here through this square of the occupation number or the occupation operator. And for this system, we can now check what is the kind of semi-classical limit. So this is a pure quantum Hamiltonian. And without discussing the details, I should mention that there's now the classical analogon, where you can write a Hamilton function, where you have, I forgot to say, we have here capital L in those sums is the number of sites. Here we have 4 sites in our system. On the classical side now, you have a phase space that is 4-dimensional, 4 sides times 2 dimensions per side. That is 8-dimensional. And you can replace the quantum operators by classical quantities Q and P, similar as an harmonic oscillator, but I think I won't discuss this in detail here. Just important, we have now the classical analogon of the quantum Hamiltonian, and this is now Hamilton function, which gives rise to nonlinear dynamics, because we have here this n, the occupations, which are where n squared includes this q squared plus p squared at each side, such that the whole thing is will be nonlinear. And then, without discussing again the details, we can now, as we did it earlier, just for the paths in configuration space, we have now a sum over paths in Fock space. And if these paths now describe classical solutions, and they are related to the mean field limit. Interference between different paths means now interference between collective mean fields or collective unstable or typically unstable modes in your system. And if the system is nonlinear, yeah, they might be unstable, and they might be again quantified, this instability, by a Lyapunov exponent. So we see, though this looks technical, it is a one-to-one analogy to the single particle case, but we simply live in a different phase space, in different Fock space. This means also that the Lyapunov exponent no longer means the instability of a single particle, but a given periodic many-body mode in your system. But this sets now the foundation, or gives a foundation, how you can relate unstable many-body quantum dynamics on the one hand to chaos on the other side. This is now truly many-body chaos. Now I have to look at the time. Steve, I forgot, when did we start? How much time is left? Just
you have a couple of minutes. You're getting close to the end. Close to the end.
I will just maybe skip part of the rest of the talk, but what I show here is now, here we have now a complicatedly looking equation that allows to compute the quantum mechanical propagator of the full quantum many-body system, however, by using semi-classical paths. And this is shown here for an example. For 20 particles, starting with a certain 20 particles at the first site, 20 at the third site, and 0 there. So 20, 0, 20, 0 is our Fock state. We let the system evolve. We project it on the initial state and see what is the return probability quantum mechanically. And this you can compute quantum mechanically, fully numerically as a function of time. And this is the blue here, this flipped blue trace with a lot of peaks showing many-body interference. Excuse me. The red part here, this comes from a pure semi-classical calculation, by the way, by Steve, showing that indeed you can use semi-classics to compute a full many-body evolution or spectrum. And if you have more particles, quantum mechanics gets exceedingly more difficult, and classical mechanics can still cope with that, or semi-classics. So this shows here, this is a prime example of many-body interference. So finally, I would like to get back to the initial question, and that had to do with the question with our out-of-time order correlator. If you remember, so here's again this fidelity. We had these 4 operators, which were out of time. I explained earlier that this is a perfect, quantity to compute or measure the stability of a many-body quantum system. And without discussing here the details, the semiclassical approach via these paths in Fock space allows indeed to compute analytically such an object under certain approximations. And this is the example, the result is just shown here. So this f here on a log scale, indeed initially as a function of time, exponentially increases. This is as in the single particle case, as in this heuristic example. So semi-classical physics, or this quantum chaos theory, predicts indeed that this many-body object should increase exponentially with an exponent given by unstable mean field dynamics. And then this Ehrenfest time that I have introduced earlier kicks in. This tells us that at the beginning, the overall many-body dynamics is mainly organized around one common mode. This is kind of mean field still. But then mean field breaks down. And then interference sets in, namely many-body interference of many different mean field modes. And this interference, as one can show, gives rise to saturation. So this doesn't diverge exponentially, but levels off at a plateau. So this has been the, say, the prediction, and this can be checked now. We stay with our system, we stay with the Bose-Hubbard system, and just consider purely quantum mechanically such an object like this F. And that is shown here at this transparency. So here for Bose-Hubbard system, we showed earlier for a certain number of sites. So we have here only 3 sites and different number of particles. As a function of time, again, this OTOC. And we see on the whole, on this log scale, a linear increase. That means an exponential initial increase, and then a saturation to a plateau. So the same as predicted here. And moreover, we see different traces. And first, we see each trace has the same slope here at the beginning. And this is just, again, I should go back here. This is just given by the Lyapunov exponent, the classical Lyapunov exponent of the many-body system, which indeed has been computed independently here and precisely, agrees with a many-body numerical quantum calculation. And then we see the crossover to the plateau at a time scale that should be the Ehrenfest time. And the Ehrenfest time was 1 over lambda times log of 1 over h bar. And here, effective h bar is just given by the particle number. So the larger n, the more classical we are, or the larger the Ehrenfest time. And that's what we see here. The first trace, the upper one, is n equal 10 to 20 up to 100 particles. And thereby this time scale where we have kind of the crossover shifts from the left to the right. So we see here, maybe to summarize here main aspect of the talk. On the one hand, the talk was relatively conceptual. So we tried to introduce a semi-classical theory, first on the single particle level, and then by analogy on the many-body level, to show how semi-classics can kind of communicate, can provide the link between chaotic, nonlinear many-particle dynamics on the one hand, and then many-body quantum dynamics. And it allows then to link the two together. And this OTOCs were the quantities that capture, that quantify instability, and indeed follow the semi-classical predictions and allow to relate an instability exponent, the many-body Lyapunov exponent, now to a quantum object like the transmon in the Google research, for instance. So I think I stop here and will, I think, skip simply the third part of the talk. I think just as an outlook without going into details here. So far we saw, I mean, to summarize, we can use indeed modern types of echoes to probe many body dynamics, to compute the stability. We understand now what it means a many body system is chaotic. We can really define this in a precise way. And well, you have the expert at your department. Steve, as you see here, these are the papers given here, the first letters, New Journal of Physics from last year, is together with Steve. And this is on the third part of here, which indeed, where we have the philosophy to use chaos not as an enemy that scrambles everything, but put things upside down and use chaos or instability as a resource. And as a resource, namely, to have an extremely fast and stable and general mechanism for quantum control. But I think that would be a nice talk by you and colleague Steve another time. Yeah. So yeah, I think I should stop here. I'm already above time. Thanks again, yeah, for listening. And I'm of course glad or happy to get questions, but maybe it's too late. Just let me know, Steve. Thank you again.
Yeah, thank you, Klaus. Do we have questions?
So maybe go back to the slide where you prepare your clock state, the 20-0-20 state.
This one?
Yes. I'm just wondering, so you're saying that these would be prepared in something like an optical lattice, right? So I'm not quite sure how a state like this could actually be prepared. Have you thought about that at all?
Yeah, so that different aspects to that. Yeah, so this is here, this is a state that is rather kind of semi-classical because we have indeed here 20 atoms in one side. Right. This is possible because you have still the, well, you can, at each side, you can tune the optical lattice such that you, that simply the side is lower, you have a kind of more, it can accommodate more particles then, if they are, they're usually repelling each other. To get such a state depends now on yeah, there are ways, in a way, your question points to the last part of the talk that I had to skip, because this is indeed one way to control, or let me say it differently. Say you start with you prepare an experiment where you have 40 particles at, say, 4 sides. So you have 10 particles in each side. Then you could use these control schemes where I didn't have time to explain how to create such a state. This would be one way, but otherwise, more generally, I'm not sure, I couldn't see who is asking the question, whether you're an expert there or not. You know, in general, I can say in the field, and Peter Engels, of course, is the local expert at your lab, for instance, there are ways, of course, to tune the optical lattices also to create states like this. So you have, I mean, there are many experiments in Munich, for instance, at the group of Emanuel Bloch, where they have what is called a charge density wave as here, where you have N0, 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 a larger array. So this is possible.
See, because as I have been doing my graduate studies, I have learned that the collisional blockade effect in an optical lattice will eject all of them except for 1 and 0. So I just kind of found that questionable.
Okay, so
yeah,
okay.
It was just I've never really seen that before. Maybe I'll look at that paper.
Do you have a comment? Okay. Karthik.
Yeah, could you go forward one slide? I think it's one slide forward. Yes, so I was just wondering what the diagrams are inside the graph, the lines that you have drawn.
Yeah. I didn't have the time to go into that detail. Thanks for the question. So the diagrams in principle tell us that there are paths underlying all the calculations. these are kind of like diagrams in a Feynman diagram way, a diagrammatic way, but you can interpret them indeed physically. It has to do with the fact that we have, if you consider this object f of t, I mentioned this out of time order. This means we have 4 types of propagation in a row, from 0 forward to time t, back to 0, forward and back. And this means there are kind of 4 paths involved in the overall propagation if you compute f of t. And if we take, I think you see my mouse pointer. If you start with a wave packet here, say this is now in a certain state, just mimicking, or it's just a sketch of a state, say a minimum uncertainty state at the beginning in a Fock space or in Hilbert space. Then you have a forward, now here forward path, forward propagation, backward propagation, forward and backward, and then you compute the overlap. And as long as you are at timescales below the Ehrenfest time, these 4 types of propagations can be well represented just by one main path, which is just, well, one of the 4. So you see the dynamics is really close to each other. So there is not real interference involved. Many-body interference appears at longer timescales. And these are the next sketch. This you should think of, you start far away, you go in a mean field solution on one path, you go, say, from here to here, and then there's kind of so you have a switch. You go from there down there to another mean field solution, and so on. And at the end, if you're back after these excursions, you acquire phases and interference. And this interference is, well, included, it arises to these phases that you see on the upper right part of the transparency. So here we have, on a level of many-body, in the many-body space, now interference of paths again. And if you compute this in an appropriate way, this gives rise to destructive interference, and thereby you get a saturation. So this is a pure quantum many-body effect.
Thank you.
Other questions?
Steve?
Yeah.
I just have a short comment that Klaus might be interested in. I can arrange to send you a paper where it turns out several years before Loschmidt, both Maxwell and William Thomson, later Lord Kelvin, talked about the same reversal effect and introduced, I mean, in a broader context, Maxwell's demon for doing the reversal.
Oh, thank you. Please just send me that. Yeah, yeah. Great. Mm-hmm.
We have another question.
Yeah, so at the bottom of this slide, say time is larger than the what's that?
The log time.
Yeah,
This log time or the Ehrenfest time. Yeah.
yeah,
Mhm.
yeah, exactly. Then the system is in the quantum, manual quantum interference regime, right?
Mm-hmm.
We really expect on the OTOF, do we see some revival or some slower decay, like a polynomial decay or something like that, or what? Yeah, what do we expect there?
I'm not sure whether I've got the question correctly. So in principle, so what this point says that for this quantity, which is this f of t, there we expect, due to many-body quantum interference, that this curve levels off, that it saturates.
Oh, it's flat.
So for instance, here, this is now the numerical example. You see, it's the same object, and this stays roughly at that level. So it won't, it relaxes kind of to this plateau.
I think I'm asking a more misleading question. Actually, I'm thinking the return probability, probably not OTOF, like the return probability.
Yes, well, yeah, it's not the return probability here. You see, it's way more complicated.
You did have a return probability in that one slide.
So we had, in a way, we had one with here.
That's a return probability.
As you see, this is, and I mean, what concerning your question, you see, there's this dashed curve, and this would tell you to what it classically would relax to. At the end, you have kind of kind of an ergodic state that has a certain overlap with the initial state.
Oh, I see.
That's the truncated Wigner line.
Okay.
And then
So this is yeah.
Do you know roughly how I can estimate the time scale of this quantum interference regime?
Yes, this is precise. What is called here tau 1 is precisely nearly the same time as the Ehrenfest time I showed here. You see, here, this time scale. It's a different quantity, but again, you see it from at the beginning, this first big hump, which is well described by what is called truncated Wigner without discussing this method. This kind of is quasi-classical. You use just mainly one orbit, one path to describe your quantum system. That works well for times shorter than the Ehrenfest time. That was precisely the regime where one orbit describes the dynamics. And then we enter into the regime of post-Ehrenfest or post-log time with all the quantum interference. And the semiclassics here numerically evaluated creates all these interference effects in line quantitatively with the quantum mechanical numerics. But if you would just take this one path from truncated Wigner, you don't get that. You cannot cope with interference there. So here we have precisely, again, the Ehrenfest time sets the time scale where kind of one path dynamics merges into many path interference.
Well, I see actually around tau 1, I see a valley. Actually the return probability almost decay to 0 there.
Mm-hmm.
Goes off. Is that?
Well, this is still kind of a quasi-classical effect of when the systems start to evolve, this 20-0-20-0 state. But already here you see oscillations you need on top of that.
That's kind of some revival. Is that?
I mean, you might call this the first peak here, kind of certain revivals, but there are way more distinct ones, like these spikes here at 4 or at 12 point something. They are really strong because this is kind of a quantum mechanical revival due to a constructive interference.
The first one's a classical recurrence. The next one's a quantum revival. It's a different.
What is tau 2? I figure.
Oh, that's the actual revival time.
Yeah, that's the quantum mechanical revival time you can roughly estimate. Yeah.
Thank you.
Do you have other questions? Jared.
Is the saturation of the OTOC, can that be predicted by random matrix theory, like analogous to the special?
Yeah. So this, yeah, Jared, great. Yeah, that's like that. Yeah. So here it is just in a fully chaotic system, it would be just random matrix theory. Here it is a bit higher than expected from random matrix theory because the system is not fully chaotic. So there are remnants of regular dynamics underneath.
For the figure of the OTOC, the saturation of that?
There, I mean, for the OTOC here, so this, yeah. So the way we derive this, we assume we do semi-classical path integrals, but we do some ergodicity assumptions that correspond to RMT. That's why we expect here this flat plateau. Also, and here in the quantum system, this is indeed chaotic. However, one can also compute, so if the system is not fully chaotic or diffusive, then you might see different dynamics here also on intermediate timescales. Then it wouldn't just be a plateau. There might be kind of power law changes still.
Thank you.
Any other questions? Well, let's thank our speaker, Professor.
Yeah, thank you again.
Thanks, Klaus.